Okay, so now let's look at how we are going to use the FFT in an algorithm. So the first thing what we are going to show is that you can compute the FFT. So we are multiplying m sub n of omega times this vector A to get the vector alpha. And we'll do this in big O of n log n steps instead of n squared, which is what we'd naively expect. Now, the way we use this for polynomial multiplication is the following. So suppose that we are given two polynomials a of x, a0 plus a1x plus a sub d x to the d of some degree d, and b of x equal to b0 plus b1x plus b sub d prime x to the d prime of some degree d prime. Now when we multiply these two polynomials, we get a polynomial of degree d plus d prime. And so the product a of x times b of x is c of x, which is a polynomial of degree d plus d prime. And we know from CS70 that if we evaluate a polynomial of this degree at degree plus 1 points, so so this is of degree d plus d prime degree, but if we evaluate it at this many points, then we can figure out c of x uniquely by interpolating. Okay, so that's what we want to do. So we pick n to be at least d plus d prime plus 1. We also pick n to be a power of 2. And now we interpret a of x and b of x as polynomials of degree n by just adding terms x to the d plus 1 and so on up to x to the n minus 1, each with coefficient 0. Okay, so now what we do is we evaluate a and b at these endpoints. So we use our FFT to evaluate a of 1, a of omega through a of omega to the n minus 1, and b of 1, b of omega through b of omega to the n minus 1. And then we compute c by computing the pointwise multiplication. So we compute c of 1, c of omega through c of omega to the n minus 1, just as by writing the product of the corresponding values. So c of omega to the n minus 1 is just a of omega to the n minus 1 times b of omega to the n minus 1 by definition. And now, finally, we use the inverse Fourier transform to evaluate C0, C1, C sub n minus 1, to evaluate C0, C1, C sub n minus 1. So we go from the values at the roots of unity to the coefficients of the polynomial. Okay, so how long does this take? Well, there are two fast Fourier transform steps. Each takes order n log n steps. There's the pointwise multiplication that takes order n. And then there's the inverse Fourier transform. But we saw that the inverse Fourier transform is no different than the Fourier transform itself. So this also takes order n log n steps. And so the entire time to multiply these two polynomials becomes big O of n log n. And that's a pretty remarkable algorithm. Okay, so now let's see how we actually compute the discrete Fourier transform in n log n steps. So remember what the discrete Fourier transform is. It's given by this matrix Mn of omega, whose jkth entry is omega to the power of jk. Right? Now, it's actually useful also to look at Mn over 2. What does that look like? Well, it's a smaller matrix, and its jkth entry is also the n over 2th root of unity raised to the power of jk, But now remember, the n over 2th, the primitive n over 2th root of unity is just omega squared if omega is cosine 2 pi over n plus I sine 2 pi over n. So remember, omega is our primitive nth root of unity, and then the n over 2th root of unity becomes omega squared. So this would be omega squared to the power of jk, which is the same thing as omega to the power of 2jk. Right? Remember, omega squared to the power of j times k, same thing as omega to the power of 2jk. Okay. You can just move this power down here. All right, so now let's see what that tells us about this FFT matrix. So the magic is going to come up by reorganizing the columns of this FFT matrix in some way. So what we are going to do is we are going to separate out into the even numbered columns and the odd numbered columns. Now remember, we can't just do that. Or in order to do that, we also have to rearrange the entries of the matrix that we are of the vector that we are multiplying it by, right? So we take the A vector and we move all the even entries to the top, and we move all the odd entries to the bottom. So this is A0, A2, A4, dot, dot, dot. This is A1, A3, A5, dot, dot, dot. Okay. So, and these columns are now numbered 0, 2, 4, dot, dot, dot. This is 1, 3, 5, dot, dot, dot. Okay, so now if you look at the jth one of these arranged columns, it'll be, sorry, the kth of these columns, it'll be 2k. And if you take the kth one down this list, it'll be 2k plus 1, right? But now remember, k is only going from 0 to n over 2 minus 1, right? So you go 0 up to twice of this, right? n minus 2. And so on. Okay, and now just to divide up the matrix further, well, let's split it up into top half and bottom half. So let's let j also go from 0 to n over 2 minus 1. So we number 0, 1, 2, so on through j all the way down to n over 2 minus 1. And then what do we do after this? When we go down, well, everything down here is going to be numbered n over 2 plus, right? So this one is going to be n over 2 plus 0. And that's going to be n over 2 plus 1, and so on, right? And all the way down to the general one is going to be n over 2 plus j. Okay, so now let's look at a typical entry here. So what's this entry here in the jth row and this column number 2k? Well, it's going to be exactly omega to the power of 2jk. Does that look familiar? Omega to the power of 2jk. So you have an n over 2 by n over 2 matrix, and I'm claiming that this n over 2 by n over 2 matrix is exactly m sub n over 2. Right? So this matrix is exactly m sub n over 2. What about this entry? Well, this is n over 2 plus j and 2k, so it'll be omega to the power of, well, what will this entry be? Well, this entry would be omega to the power of n over 2 plus j times 2k. Well, this is omega to the power of n times k plus 2jk. But remember, omega to the n is 1, so omega to the n times k is just 1. So you can just pull that out. So this is omega to the n times k times omega to the 2jk. But that's equal to 1. So it's just omega to the 2jk. Meaning this is also m sub n over 2. So just by rearranging these columns and putting the even ones first, we got m sub n over 2, m sub n over 2. Now, what are these two pieces going to look like? Well, let's look at it. So what's this entry going to look like? The j 2k plus 1 entry. Well, what we'll get here is omega to the power of j times 2k plus 1. So you get omega to the j times omega to the 2jk. So that's not quite like the m sub n over 2. But what we are saying is it's m sub n over 2, except that the jth row is multiplied by omega to the j. Not so bad. And what about this entry? Well, you'd get, now instead you would get omega to the n over 2 plus j times 2k plus 1. And if you simplify it out, basically this n over 2 and 2k is just going to give you nothing. And so you'd get omega to the n over 2 times omega to the j times omega to the 2jk. And omega to the n over 2 is minus 1. So you'd get minus omega to the j times omega to the 2jk. Okay, so our matrix, we can write it in shorthand like this. So m sub n is m sub n over 2, m sub n over 2, omega to the j, m sub n over 2, minus omega to the j, omega to the j. Sorry, this should have been an omega to the j, m sub n over 2. Okay, now this has a lot of implications because now remember what we want to multiply it by is this vector, which consists of a even, a odd. Okay. And so how do we do this? Well, let's give ourselves some space. So what we've ended up with is with this matrix, which looks like m sub n over 2, m sub n over 2, m sub n over 2 times omega to the j minus omega to the j times m sub n over 2. And we are multiplying it by this vector, which we split into a even and a odd. And so what we're going to do is we'll just compute m sub n over 2 times a even. This is a vector, that's a vector, right? So let's call this vector u, and we compute m sub n over 2 times a odd, and we call that vector v. So we now get this vector u, which is u naught, u1, u sub n over 2 minus 1, v, which is v naught, v1, v sub n over 2 minus 1. And now, what should our result be? Well, look, out here we get a even times m sub n over 2, that should be u. And then we should get a odd times m sub n over 2 times omega j. So we'd get omega j v. Right? So that's the top half of the vector, and the bottom half would be u minus omega to the j v. Okay, so let me write this out in greater detail just so you can see what it is. So the first entry is going to be u naught plus v naught. The second entry would be u naught plus omega v naught. The third entry would be u naught plus omega squared v naught. Oops, sorry. This would be u1 plus omega v1. This would be u2 plus omega squared v2, and so on up to u n over 2 minus 1 plus omega to the n minus 1, n over 2 minus 1, v n over 2 minus 1. What about down here? You'd get u naught minus v naught, u1 minus omega v1, u2 minus omega squared v2, and so on. un minus 1 minus omega to the n over 2 minus 1, v n over 2 minus 1. Okay, so let's see how long it took. Well, how much work do we have to do? Well, the time required to solve this problem on an instance of size n is, first we have to sort into even and odd. So we have to separate out the indices into the odd ones and even ones. That takes order n time. Then we go ahead and take the even part of the vector and compute its FFT recursively. So that's t of n over 2. We take the odd part, we compute its FFT recursively. That's t of n over 2. So we get 2 times t of n over 2. And then we take these two vectors and we take their sums and differences, multiplying this, the jth entry of v by omega to the j. So that takes order n time to multiply, and then multiply by the appropriate power of omega, and then add and subtract. So that still gives us another order n. So t of n is 2 times t of n over 2 plus order n, which means that t of n is big O of n log n. Okay. So if you unwind this recursion, all you're doing is you're just separating out into evens and odds. Then you're doing a recursive call, right? So that just keeps going on and on. So you keep recursing, but then when it comes back to you and you get these answers, all you have to do is add and subtract. Okay, so that's the FFT algorithm. And okay, that's it.